Swayam Prabha. Digital India. Educated India.
Welcome to the 12th lecture of this course on transport phenomena. This is going to be the last lecture in fluid flow section. So in the last lecture we talked about compressible flow. In this particular lecture we are going to conclude with showing how to extend our analysis to more general cases. As you may have noticed, so far we have been looking at multiple examples, or sort of a standard flow. For example, flow through a circular tube, flow over flat plate, flow through packed beds, and so on. So these are very specific examples in fluid flow that we have looked at. In this last one, we'll talk about how to. So far we have looked at specific examples. In this last lecture on fluid flow, we'll look at how to generalize it further. So with that, let me share the slides. As in this one, we'll first look at generally our focus is to look at balances in 3D, and we'll limit our discussions to what happens in Cartesian coordinate system. Of course, similar generic expressions are available in other coordinate system, for example, in cylindrical and spherical, and those you can look at in the textbook. Okay. So we'll first do the mass balance, and also from there we'll get the continuity equation. Then we'll do the momentum balance, and then what you may already be aware of, this generic equation in fluid flow is actually the Navier-Stokes equation. So we'll look at it. Essentially, we are looking at the origin of Navier-Stokes equations in this lecture. And then we'll deal with one examples of one application of Navier-Stokes equation, so that you get some idea about how do people generally apply these equations to some standard problems you have already seen. We'll talk about flow over flat plate, but this time in the stress perspective. Okay. So with that, let us relook at let us relook at this generic equation that we know, that any conservation equation we can write as rate of accumulation can be said as rate that is coming in, and then rate that is going out, plus if there is any generation term, etc., and so on. Okay. So we will apply this simple principle now to we'll first do the mass conservation, and then we'll do the momentum. Okay. So the system that we are going to talk here is actually we want to do the analysis in 3D, but for the sake of simplicity, sometimes it's difficult to imagine things in 3D. So we'll do in we'll do discussions in 2D, and then take extrapolate our equations to 3D. Mathematically, I feel it's easier to extrapolate, and it's easier to imagine in 2D. So what we are going to do is, instead of looking at cube, we'll look at square. So just to remind you, we'll look everything in from a Eulerian point of view. That means you have some fixed frame of reference, so x, y, and I'll also show you later there is some connection between Eulerian and Lagrangian in this discussion. So what we'll do is, typically we'll take some point at x, y, and by extrapolation you can see that this point in 3D will be x, y, z, and then you go to some delta x here, delta y here. So what you will have is essentially x plus delta x, y plus delta y. Okay. So and then we are going to discuss fluid flow that is something like this. Not the standard type of flow that we have looking at very well aligned along x direction or along z direction, whatever. But in this case, flow is in some arbitrary direction, and such that your control volume or control area element in this case is not aligned to the flow. So this is the flow situation we are going to deal with. Okay. So in this flow situation, we would like to see, this is your y, this is x, so this is your delta x, this is delta y. Okay, so you have some flow like this. Okay, so we know the general conservation principle is going to remain same, right? So what we do is we look at term wise. So in this control area, if you want to write what is the accumulation term, so it should be some mass that is in there. So it should be some rho delta x delta y, and if I extrapolate this to 3D, then you write it delta z, or otherwise if you want to do 2D, then you multiply by 1. So this is your accumulation term. Then rate of this thing coming in, so that means whatever is the mass coming in is in this direction at this surface, that is what you want to write. Okay, and then what is coming from here. Okay, so it will have an sort of, you can imagine it as two components. So first, as you want to write at this surface. So at this surface, your this thing will be rho times this this area. So rho AV we are trying to write. Mass flow rate is rho AV. That is what we want to write. So area is your delta y, and again if I extend it in 3D, then there has to be delta z, and then you are concerned with Vx. So only what you do is you have this flow, and then you take a dot product with area vector, or so you will have just rho AV, A dot V. When you do, you will get Vx. Okay, and we'll specify the location. So this location is your x, y, z, and when we are talking about going in from here and coming out from here, you can consider actually the average here. So that will be y plus delta y by 2. Here also y plus delta y by 2, but that term does not change. So we can just write that whatever is coming in at x. Similarly, if you look at this surface here, then you have density. Here your area is delta x, and then you will extend it. You will extend it, so that will be delta x and delta z, and then you will have some Vy. Again, you are taking dot product, and that you can say at y. Now, since as I was saying, we are doing in 2D, but if you extend it to 3D, you will have one more term. Okay, so in cube you have 6 surfaces, so 3 will be coming in, 3 will be going out, right? So this will be now delta x delta y. You can see the pattern: delta y delta z, delta x, and then delta x delta y, and then you will have Vz z. So now we want to write the out term. Okay, so out, whatever is coming out, so this term, whatever is coming in from this surface and going out here, so this you can write as rho delta y delta z. That area remains same. So here you will have what V x, but now this is, if this is x, this is x, and this is your x plus delta x. So now this will change from x to x plus delta x. Similarly, for other things also, you can write rho delta x delta z Vy, y plus delta y plus delta x delta y, and then this will become z, delta z. Okay, so this is in, this is the mass coming in, this is the mass going out, and this is your accumulation term. But we actually talk about rate of accumulation, so you have to do del by del t. So we should have del dou rho by dou t, right? Then you have volume term. So this is for your given control volume. This is same. So this thing delta x, delta y, delta z times this density. So what you can see is this is going to be equal to, this term is going to be equal to this minus this. And if you see here, for example, let us look at just these two terms. Let me change the color here. Yeah, so if you look at these two terms, you have delta y, delta z common. Similarly, if you look at these two terms, you have delta x, delta z common. And if you look at here, delta x, delta y common. Okay. So now if I divide this whole in minus out term by this volume, then you can see that we can write net equation as dou rho by dou t. And then here you will have rho. If I'm dividing by all of this, so then you can write Vx at, you have to do we can do minus here. So then you can write x plus delta x minus Vx at x by, you're dividing this thing by all three of his, so you will have delta x. So this we can write as dou Vx by dou x. Okay, remember that this we are using everywhere the partial derivative because things are changing in all three directions, and also density is changing with respect to time. Okay, so velocity also is maybe as we look at it, if you are solving transient problem, then velocity also is a function of time. So we use partial derivatives here. Okay, so now we can also see that density is common in all six terms that you have written here. So we can take this common, and you can actually take minus of density common, so that you can write out minus in, because that gives you the derivative. Okay, so from here onwards we don't write this equation. Let us write it as dou Vy by dou y, because you are dividing this delta x, delta z by delta x, delta y, delta z. So you'll have dou y, and all this minus sign is already taken care of. So this will be dou z. Okay, so this also now we can actually, based on this discussion, we can actually remove all of this, and just to make it look a little better. So this will become your the Vx by x, and then you had minus rho. Okay, so this is the mass conservation equation in 3D. That is how it looks like. Okay, yeah, we can make it even, bring everything together. Okay. Yeah. So this is also known as equation of continuity. So now once you have this, so if you have constant density fluid, then what you can do is you can say dou rho by dou t, that is going to be 0. If you do that, then you can write, you can see that other things will this is 0, so this you can remove. So you can write this as dou Vx by dou x plus dou Vy by dou y plus this is equal to 0. So at this point, I would also, some of you may already know, but I would also like to introduce this del operator. So del operator is, you can write as del by del x, dou by dou x, and in I cap, so that is unit vector in x direction, and so on. So you can write dou by dou y j cap plus dou by dou z k cap Okay, so now you can see that we can add for this constant density fluid, we can write equals 0, right? If you take dot product of this with the velocity vector, you would get this. Okay, so this is your equation of continuity. If your density is constant, kind of incompressible situation. Okay, so this is how you can. So this is so now we conclude the mass conservation or equation of continuity. So we'll move to momentum balance. So as usual, we'll look for terms. We'll do accumulation equals in minus out plus anything. In minus out plus if there are some external forces and so on. So let us first look at this accumulation, or you can say this as rate of change of momentum. Okay, so you can call this rate of change of momentum of your control volume. Again, we'll do the same thing. Remember, we are talking about situation in 2D for the sake of understanding, and then we are extrapolating it to 3D. So again, we have the situation where you have this flow rate. So fluid flowing through this volume, and this is your x, this is y, and this is delta y, delta x, and so on. Okay. So first we'll look at the term delta x, and in the case of momentum, since it is vector, we'll first look at only in x direction. Okay, so you can see that there are two levels of simplification we are talking about. We'll first analyze the situation in 2D and extrapolate it into 3D, but all of this we will be doing for momentum only in x direction. Okay, so here momentum, rate of change of momentum can be given as m dot v, right? Yeah. So let's first try to write this term m dot v, or dmv by dt, or whatever way you want to understand it. So dmv by dt you want to write. So m is rho times whatever is the volume. So delta x, delta y, and now we extrapolate to 3D. So that's delta z. So that is your mass, and then velocity in x direction is vx. Okay. So this is your mv term, but you want to have a differentiation of this. So what you can do is essentially you can write delta x, delta y, delta z, volume term is outside. Then you have rho vx. So then you will have again partial derivative dou by dou t of this term. Okay. So now if you say it's constant density in compressible flow, and your density is not changing during the flow, so then you can bring that out. So for constant density, we can write rho delta x, delta y, delta z, dou vx by dou t. Again, this is in x direction only. If you want to write y and z, then it will be the same thing. One can write as dou vx by dou t plus dou vy by dou t, and plus dou vz by dou t, and so on. Okay. So far so good. So we are writing x momentum. So now we have to do go term by term. So terms of as usual, we talk about advective term. This is due to bulk motion of the fluid. So since due to bulk motion of fluid, it is carrying momentum, and in heat transfer we will say it will carry temperature, and in mass transfer you can say it is carrying concentration. So you can also see the generality of this analysis will come out at the end of it. So you will have some advective term. Then you will have some contribution from the molecular part, where viscous dissipation. So you will have shear stress term. So you can have a viscous term, and then you have a pressure term, and then you have you will have in this case gravity term, and if you have any other forces, you can have any other forces, but we will not consider that in this discussion. Any other forces, you can have electromagnetic forces, you can have electromagnetic forces you can have sometimes. You may want to sometimes consider surface tension related forces and so on. So this term will contain those things. But here our interest is this. So as usual, we'll look at term by term. So we are first looking at advective term. Okay. So advective term, again what we'll do is we'll write in 2D and then extend extrapolate it to 3D. Okay. So in this situation, we want to write what is momentum going in from these surfaces. So momentum in we can write as, so first we want to see how much mass is going in from this surface, and that we know from this discussion here how much mass is going. So we know this one, rho delta y delta z vx, right? So rho delta y delta z times vx. So this is the mass that is going in, and then we have to multiply that mass with x component of the velocity. So this mass times velocity, that will be vx. Now if you look at this surface, the mass that is going in, what we discussed was rho delta x delta z times vy. So this will be rho delta x delta z times vy, and then we are just concerned about x momentum. In totality there will be y and z momentum. Also we'll look at it. You can generalize it later, but right now we're concerned only about x momentum, so that will be vx. Similarly, now we extend this, what we discussed, this to 3D, then we will have rho delta x delta y, and the mass in that case will be vz. Okay. And then you will have again here x momentum is vx. Okay. So similarly you can write an out term. So out term again will be the all these things we talked about at x, and so on, right? Yeah. So we talked about y and we talked about z. Okay. So similarly, when you can go and write the same thing, but on the other side of it. So that will be vx at x plus delta x, and then so on, right? So rho vy vx at y plus delta y, and rho z plus delta z. Okay, so now we want to do in minus out, and let us consider a situation where your rho is constant, and what we do is you have to take this minus this. So just let's look in little detail about. So if you do this in minus out, so what we can do is you can totally see that rho is your constant, so this will be outside this thing, but these two terms here, these two terms here are at x plus delta x, and here it's x. So if you subtract it, and if you could divide it by delta x, if you multiply whole thing by over here also delta x, and you do delta x here, or also you do delta x and then divide it by delta x. So then you can see that this will become first term. If you look, this will be a rho delta x delta y delta z, and then it will be vx at x plus delta x minus vx at x, and then you have this delta x in division. So what you will have is rho delta x delta y delta z times partial derivative vx by x. Okay. So we can write that. Similarly, if you do this thing for these two terms, then you will have two more terms. Again, rho delta x delta y z will be common everywhere. So here now you can write rho delta del vy vx or vx vy del y plus here you will have vz vx, or yeah, we should write that way. So rho vz vx by z. Okay. So this is how, this is the your in momentum in and minus out for the advective term. Okay. So in the next what we want to do is, if you want to break these things, let us actually focus on the term in the square bracket here, this plus this plus this, just a little bit, and then we can so what you will see if you try to break this, because you can use the product rule here. So if you use the product rule here, then del vx by del x you can write as vx del vx by del x plus vx, and in this case it's a square. So similarly you will have other terms. So for example, if you look at the next one, vx vy by del y, in this case it will be this vx vy by y plus vy this thing, and then you have one more that you can write as let's write it other way, x here, z here, z here, and x here. Okay. So now if you, in this term you want to add everything, so now if you go to your continuity equation, you will see that this some of these three terms are actually 0. So del vx by dou vx by dou x plus dou vy by dou y plus dou vz by dou z is 0. So what you can see is here you have all vx here, then you have dou vx by dou x, dou vy by dou y, and dou vz by dou z. So what you can see is so this term over here is actually this is going to be 0. So then you have sum of all these three terms will be only this. Okay. And please note that you should have a minus sign here, right? If you are doing in minus out, then you should have everywhere the minus sign should be there. Okay. So advective term, then that means we can write as this. Let me show you. This is what you can write as advective term. So this is your rho dou x dou y delta x delta y delta z. Then you have vx dou vx by dou x plus vy dou vy dou y, and so on. So this is the term here. Okay. So this is then you're done with this. So minus rho delta x delta y delta z, and then over here you have this whole thing. Okay. So this is your advection term. So remember we just did the simply in minus out, and we go term by term, and then you are able to get it. Okay. The second one is you want to look at is the constitutive equation that will be there. So what you have to do is, in this case you are actually looking at let's use the different color. Okay. So here here you want to consider the second term, that is viscous dissipation. So here you have to use the constitutive relationship, and again what we do is we write it, we'll write we'll try to write it in 2D and then so on. Okay. So this is how, you know, again you have flow like this. Yeah. So again we'll do in minus out. So in this case you have you know two surfaces here when we are looking in 2D. So this surface and this surface. Over here also, since you know shear stress is because of the change in you know change in velocity. So you may have since you will have some dou Vx by dou x, so you will have some you know some shear stress, you know some momentum transfer rather in some momentum transferred in x direction, and you have to consider that momentum transfer that is due to viscous dissipation. You know, and that happens because of viscosity and velocity gradient. So that in term you can write as, you know, for that surface tau xx. This is because of this term. Tau xx can be and then you have to multiply that by area, so that we know delta y delta z. Now on this surface, what you are going to write is tau yx and then the area is your delta x delta z. And now if you extrapolate it, you will have, you know, tau yx is, you know, momentum transfer in y direction because of velocity in x direction. Okay, so tau yx, if you recall it goes with dou vx by dou y. Okay, similarly you will have tau zx, again dou vx by dou z. It will be related to, so this will be delta x delta y. Okay, and again, you know, you can do x y and z. Okay, similarly your out term will be tau xx delta y delta z and x plus delta x y plus delta y so on. Okay, so now you again you want to do in minus out, and as usual we can now, you know, that you can multiply this by delta x and divide by whole thing by delta x, so that you get it in the differentiation form. So if you do all these things, then your in minus out term will be minus delta x delta y delta z, and then you will have dou by dou x tau xx dou by dou y tau yx plus dou z tau zx. Now we know from you know when we're just talking about 2D, and you just you know, when you had one dimensional flow only, you know, recall the initial discussion about Newton's law of viscosity, when you have this fixed plate and then you have some fluid flowing, so you know, your plate is moving at some v naught, and so you have some you know, some momentum transfer in this direction, right? So in this case, you know, we saw tau yx is just you know minus mu you know minus mu dou vx by dou y. But if you have you know, if the plates are, you know, if you look at the fluid element which is free to flow, and the flow is not only in this direction, rather, you know, it can be in any arbitrary direction. So if you see it here, for example, you know, this highlighted portion, you know, initially may be here, and then it may, you know, so it may deform and you know, it may deform to something like this. Okay, so initially you will see that, you know, your fluid element, for example, is fixed here. If you look at fluid element, it was changing like this, right? So now so we are only concerned about this deformation. Now if you let it you know, if it was not fixed here, it could move in the other direction. So that this is why you get, you know, this was your usual one, and now you're getting this additional. So what happens is you have to consider this both, and you know, so here you're getting one gradient, and then you will get another gradient. So here you are getting dou vy, you know, by dou x. Here this will be due to dou Vx by dou y. So under these circumstances, you typically give tau xx as sum of these two terms. So that is true for all of it. So you will have tau xx is typically you can write as minus 2 mu dou x by dou x, and tau xy and this is typically equal to tau yx. For mechanical equilibrium calculations, if you have done a course earlier, you would know. But let us say in that these two are generally equal. So that gives you then minus mu. And now you have to take both term in the consideration. So you will have dou Vy by dou x plus dou Vx by dou y. Okay, and similarly tau xz, or sorry, this will be xz. Let's be tau zx, and this will be minus mu. Again, you have to have the two terms, dou Vz by dou x plus dou Vx by dou z. So this is the origin of it, but more detailed, we don't have time to discuss that in this course, and it's not as long as you understand that what is the origin, that is enough. Okay, so now you have to do in minus out, and you have to substitute all these things in this equation. All of this has to go there. And once you do that, we'll not go into derivation, and we again use the continuity equation, that is your del Vx by del x plus del Vy by del y plus del Vz by del z equals 0. Once you substitute it there and use this equation, what you will get is your viscous term is actually will come out to be. And again, what you will see is you have a minus term here and you have minus term here, so they will cancel out. So these two minus term will cancel out. So this one and then this one, or this one and this one, this one and this one will cancel out. So what we'll have is again in minus out. In this case, you will have as delta x, delta y, delta z, and then you have viscosity. And remember, all of this we are doing this for Newtonian fluid. So if you have some other type of fluid and that has different relationship with shear stress and elastic gradient or visco, and then you have to consider that. Okay. What you will see moreover is that in this side you will have just Vx term, which intuitively makes sense because we are talking about the momentum transfer due to x component, xx component of momentum. So you should have a square here. Okay, so this is your this term. Now third one is the pressure. Okay, so pressure term is relatively straightforward. So you will have pressure here in x direction. So pressure does not it's same in all directions at a given point. So that way you can write delta y, delta z is your area, and pressure at x minus pressure at x plus delta x. So again, this if you do it, you may write it as delta x, delta y, delta z. Then this will become you want to write it that way, so you will have minus delta p by delta x. Then the last one is your gravity, which is mg. So m is your rho times delta x, delta y, delta z. And now g, you have to take component y. So what is the component of gravity in this particular direction? So that is your gx. Okay. So these things are rewritten here. So advection term we found this, viscous dissipation we found this, and then the pressure term is equal to this. So and the gravity term was this. So now what we have to do is we have to bring everything together along with your rate of change of momentum term, which is here. So what you will see is delta x, delta y, delta z is common in all of it. So you can just forget it. So all these are gone. So you can write it in this form. Dou Vx by dou t. This comes from your rate of change of momentum term, and then you will see that this advection term is negative here, so we can take it to the left side, so that gives Vx dou Vx by dou x and so on. Okay, and then you have this as viscous term, then you have the pressure term, and then you have the gravity term. Okay, so I would just like to introduce a term here, which is called as substantial derivative. So to represent this thing as one term, what you call this as substantial derivative, and you then write as rho d. In this case, we are talking about substantial derivative of dvx by dt. You generally represent it by capital D by dt. What it physically means is the when you're looking at the change in velocity in this case, if you're looking at the change in velocity in Lagrangian frame, then you can see rho dv by dt. You can write as dvx by dt. You can write this as d by dt. Just that's fine. Okay. This is known as substantial or material derivative. We unfortunately don't have enough time to go in detail of this, but just to give you physical interpretation, this means that how would one see if so for example, if you have a fluid packet here, you can either fix a frame here, or rather, let's think this way. If you have a flow here, either you can fix a frame on the bank on here, and then you look at this fluid. You have this control volume, or so you see how the fluid is moving past this. So this frame is fixed with respect to the origin. Of course, the other way to look at it is you just take a boat and then you actually go with the stream. So just you're moving at that same velocity as water, and then you observe the changes along it. Okay. So there are many ways to look at it, and if you want, you can read in textbooks what it actually means. But let's say you're looking at something material. Let us say you're looking at some concentration of some chemicals. There could be a plant here and it's releasing some chemical, and if you want to look at this concentration at this particular point, or let's say at this particular point where you had this earlier Eulerian frame, and this guy who is moving along with the boat, and when he or she reaches here, that person will find that both whether you're looking from the lab or your friend is looking from the boat, both of you will find should find the same concentration. So that is the meaning of this term. So that change overall derivative is given by this term. All of this if you are in the Eulerian frame. But you can just write by dvx by dt, because in this case your flow is you're not moving with respect to flow. In this case your frame is moving with respect to flow. So that's the difference. So in Lagrangian frame you can just write rho dv by dt. When you're in Eulerian, you have to expand it, and the relation between these two frame of reference is given by this. And this is valid as we are just looking at. We're looking at the concentration. It is valid for any quantity if you are doing this kind of balance. There's some comments on Navier-Stokes equation. So what we looked at is there are 4 equations. One is your continuity equation, and then you have three from your momentum balance. We did derivation for one, but you will have similar equation in y and z direction as well. So you have 4 equations, and for constant density conditions, you typically have 4 unknowns as well. In this, you want to know pressure at the point, and then you want to know Vx, Vy, Vz, right? So it should be possible, theoretically, to solve and find out these 4 unknowns from the four equations. But the equations are linked, and there's no general solution available for such cases. Only specific solutions, under certain boundary conditions are available. So there is no general mathematical solutions available yet. There is, it's one of the hot topic of research in mathematics, and it's kind of $1 million problem if you if you can find a general solution and so on. In under specific condition, as I said, analytical solution is possible, and we'll look at one example as follow up to this. And but commonly, what we do is we find a numerical solution. Okay. So commonly we will have numerical solution. What do we mean by numerical solution? Is you discretize these equations and then you put in the form of matrix, etc. We'll discuss not of these equations, but some numerical solution related thing in heat transfer. And when you can do the numerical solution, and this is what is used in this computational fluid dynamics. So transport phenomena is in kind of study of transport phenomena is incomplete in modern times without CFD. So in CFD, what you typically do is you discretize equation and discretize the equation, and then you find some numerical schemes and all those things you do. Moreover, you can also use the Navier-Stokes equation to model turbulent flow. So what for the derivations we didn't go into in turbulent regime. We talked about only laminar conditions, but you can model this turbulent flow as well. There are many models available for that so that you can change, for example, viscosity in this case and so on to model the turbulent flow. Okay, so it's very important equation, and that is why we did some derivation at least to give you an idea of where it comes from, and we'll see at least one example. We'll see how we can implement it for analytical solutions. Numerical we don't have, that will be some advanced transport or some other course. You can look at mechanical engineers or even chemical engineers. They also do these things. For our purpose, I think as long as we have idea of how these things come, where it comes from, and if needed, we can implement it in some practical problems. That is what we need. So I hope that you got some idea where this Navier-Stokes equation comes from. So with that, there's a simple practice problem, kind of revisiting what we already saw. So in 2D, that means in XY system, X momentum balance at the steady state we are talking about. So steady state, so you can make, you can say rho by dou t is 0. Maybe written as, so how can you write it? So you will see that it looks similar and signs are here and there. I want you to go through the options so that you get familiarized with the equation. So it's just written in different format. One thing to look at is you have signs different, and another thing to look at is whether it should be Vx Vy or whether it should be Vx Vx similarly on this side. Okay, so based on the discussion, you should be able to answer this. Okay, yeah. So maybe you can pause for a minute and then do. Yeah. Okay, so so we'll now look at the one simple example, application of Navier-Stokes equation. So just remember this, you have 4 equations, and those are partial differential equations. It's difficult to solve, so you want to simplify those equations. Okay, so for example, in this case we'll take an example of flow over a flat plate. We have looked at this problem, and we didn't go through complete solution. Here also we will not be able to go through complete solution, but we'll at least do the problem setup. Okay, so you are aware that if you have this fluid flowing over this solid plate, which is stationary, you call this velocity V infinity. And so there will be some formation of boundary layer formation. We know that. Okay. because of fluid interaction of fluid with the solid surface, there is some friction term coming up, and then you have some due to viscosity, this information will get will travel in the bulk. So you will have this boundary layer which will keep increasing along with x. Okay. So we would like to we would like to go back and we would like to write the mass conservation and momentum balance equations, etc. for this situation. To start with, we would also like to simplify on the way, but we don't want to oversimplify. So whenever you have, we make some assumptions about the problem to simplify it so that you can solve. But keep in mind that you don't want to oversimplify that, to an extent that it changes the problem itself. So we still want our, even after your assumption, we want the problem, the setup, whatever assumptions you have made, and the problem that you have, you have some problem and then you modify it with these assumptions. So modified version of the problem should still be related to your original problem. That is what I want to say. Okay. So here, for example, let's say your Navier-Stokes equations is in 3D. So first assumption you can say is that here the important dimensions are x and y. Z width of the plate is not as much important. So x and y. Okay. Right. So and even in the y, our region of interest is whatever is delta. So that is the boundary layer thickness. Of course, delta is function of x. So but this is our region of interest. We are whatever happens here. Actually, nothing much happens here, right? It remains v infinity. It's constant velocity. It's just going on. There's not much happening here. Okay. So this is our region of interest as well. So from our description of problem that we have discussed earlier, that velocity, so here you have zero velocity because of no slip condition, and at all this boundary layer defines as locus of points having velocity equal to 99% of v infinity. Okay, so that means that velocity, if you look at the Vx over here versus Vx over here, you can say that the Vx over here is typically the gradient is del Vx by del y is much larger here compared to here, or you can also say that Vx here is much larger compared to typically the Vx you will have here. So Vx changes in x direction. So if you look at your continuity equation, and we say that rho is constant, so del Vx by del x, and this is not equal to 0. We know it from our understanding of the problem. So that also means that this del Vy by del y will be there because some of these two are going to be 0. This is not 0, so this also cannot be 0. And we know that the Vz we are not interested in, and that we don't expect any flow parallel to the plate in the width direction. In the length direction, there is of course flow parallel to the plate. We don't expect the we don't expect the flow to be flow in this direction, right? In the width direction, we don't expect. You expect here, and there could be some velocity gradient in del Vy by del y. So Vy fluid may be moving in this direction, upward direction, and that gradient may change. Okay. So other assumption is this is other simplification rather is regarding pressure. So since fluid is flowing in the bulk at constant velocity, so V2 square means V1 square is 0. There's not any change in kinetic energy. So we don't expect any change in pressure. Okay. And since the boundary layer thickness is so small, we don't expect any change, in pressure with respect in x direction either. So what we can say is del P by del x is equal to 0. Is negligible. And since you have horizontal plate and the gravity is in downward direction, so Gx term is also 0. So with these assumptions, now we can write now we can write the momentum balance equation. So in x momentum we can balance, and since steady state we are talking about, so you know, so we are you know, we are interested only in this state. So what we can write is dou Vx, you know, dou by dou t term will be 0. So dou Vx by you know, Vx dou Vx by dou x plus Vy dou Vx by dou y, and then that should be equal to your mu. We are not considering the z term, of course, as we discussed earlier. Okay, so now if you look at this term by term, what if you look at the variation of, you know, variation of this term and this velocity, variation of this velocity dou to v by dou to Vx by dou y squared versus dou to Vx by dou y squared. If we can compare these two things, and if you look at here, you know, Vx in x direction, it does change. It does change from here to here. It does change in the boundary layer, but dou Vx by dou y, if you look at, you know, the boundary layer thickness is so small, and then it goes from 0 to V infinity in this small thickness. So this change is much more pronounced than dou v by dou x. You know, change in this direction is much slower than this direction, because boundary layer thickness is so small, right? So if you use this argument, then what we can say is dou to Vx by dou y squared is much greater than dou to Vx by dou x squared. Okay. So what essentially this means is that we can ignore this term. This is almost equal to 0. So you will have Vx x dou x plus Vy dou x by dou y dou to Vx by dou y squared. So this is the equation you would like to solve. Okay. And so this is the equation you want to solve, and you know, we are not going into the details of solution, but it involves, you know, converting this to you know, right now it's partial differential equation, so it involves converting this to ordinary differential equation, you know, where you can add d by dx instead of dou by dou x. So you convert it to ordinary differential equation, and there is a method by Blasius that describes how to do that solution. And you know, so when you do this conversion from partial to ordinary differential equation, it turns out to be a third order ordinary differential equation, and you know, to solve that you need 3 boundary conditions. So you know, boundary conditions for this plate, we know that at y equals 0, that means at the plate surface, what you can see is, you know, complete velocity is completely 0. So you will have Vx equals 0 and Vy equals 0. So that gives you two conditions, and then you know, at y equals infinity, that means you are talking about here beyond this. So we know that Vx is equal to V infinity, right? So from here you have three boundary conditions, and then you solve that third order ordinary differential equation using the method by Blasius. So from there you can actually show that, you know, delta is always equal to this. No, this is not velocity. This is kinematic viscosity times x by infinity. Okay, so we have, you know, this mu by rho, so rho v, you know, so we know that this is 5 by square root 5x, you know, so we have looked at delta by x is equal to 5x by 5 by re, right, square root re. No, if you do, you know, do that, you can rearrange this equation to find this. Okay, so this solution actually comes from this analytical method. Of course, for laminar flow, So this was just one example, like, just to show you how to how to use Navier-Stokes equations to some problem. All you have to do is you have to start with the basic set of equations, and then you make some realistic assumptions to simplify your problem, and then even then the mathematical the solution of differential equation is not so easy, but it can be solved for standard cases. And then you can find velocity profile, you can find delta boundary layer thickness, and all those things calculations you can do. Okay, so with that, there's just some concluding remarks regarding this. So similar examples is possible in other geometry. For example, you can use this set of equations to find flow in entry region of circular tube. We have done derivation for laminar flow in fully developed region using our energy and using our momentum balance earlier. But you can use you can directly start with these equations in cylindrical coordinate, and then come up with this. You can also do this the derivation for Stokes Stokes velocity for creeping flow around a sphere. As I said earlier, you can use it to model turbulent flow. And even more general, for heat transfer and mass transfer problems, you have to solve the coupled equation, because under these conditions, if you have some temperature gradient, your viscosity can vary, your density can vary, and if you have even the concentration changes, then also your density and viscosity can vary. So very often you have to solve this as coupled problems. You will have similar equations. So here you had equations for velocity, then you will have in heat transfer you will have equations for temperature, and in mass transfer you will have equations for concentration. So then since those things become more interrelated, so you have to solve accordingly. So that's even more challenging. So very often we implement all these things in computational fluid dynamics. So if you are interested in that area, you can take some project in that and so on. Okay. So with that, we conclude our discussions on fluid flow. From the next lecture onwards, we'll look at heat transfer, and you will see that heat transfer and mass transfer are similar. So we may not have enough time to actually deal with mass transfer, but I'll point out the similarities wherever it's possible, where between heat transfer and mass transfer, so that you have an idea of that component of transport phenomena as well. So with that, thank you.